As I wander through this paper birch forest, I wonder how hard would it be for me to put sensors out here. So you probably know I'm into all things data, sensors, home automation, and the outside world is just something that's kind of hard. So some examples you might need: if you're into gardening, you might want to have soil sensors or moisture sensors outside, long distance from your house. Maybe your mailbox is far away across the street, you want to monitor that. House is all the way back there, not going to get Wi-Fi out here. Zigbee and Z-Wave probably aren't going to work either. 433 megahertz has its own quirks. What if there was a better solution for long-range outdoor sensing at home? And that solution is LoRa and LoRaWAN. So in this video, I'm going to set up a full-on LoRaWAN network. The gateway, the cloud, the sensors, the decoders, and get all that data into Home Assistant. So come along with me on this adventure. So, to aid in my exploration of LoRa, Electro was kind enough to send over a few goodies for me to try out. So here's all the stuff I got. Temperature and humidity sensor, capacitive soil moisture sensor, in case you need to do some data logging in your garden, light sensor, that could be useful, LoRaWAN hat, LoRaWAN Gateway. So this is a LoRaWAN node module. So this node has a LoRaWAN node module and an RP2040, that's the Raspberry Pi Pico MCU. And it has a bunch of ports for sensors. They sent me some sensors to go with it. And the star of the show, LoRaWAN Gateway. So this is the LR1302 LoRaWAN Gateway module. And then this should be the hat. And it is. So this is the hat. This goes on top of a Raspberry Pi. It's got a built-in GPS module and a slot that fits the LoRaWAN module. So these two guys talk to the Pi, and we get a full-on LoRaWAN Gateway. So this guy is going to go here, and he's got a built-in fan to cool my Pi. Gateway module goes in here. This is not actually mini PCIe. It's using the same connector, but it's USB, SPI, and I2C. Get in there. There's a very tiny little RF cable. Okay, got it. So this is the LoRa antenna. This is GPS. GPS guy's under there. We'll jump up to the LoRa board. So now we got the board set up. Got my antennas ready to go. Just got to set up the SD card. So after a quick trip to Raspberry Pi OS Imager, I set up my LoRaWAN gateway in my cat's bedroom, and he is disappointed to lose that end table. So I might be getting a little bit ahead of myself now. What is LoRa anyway? Well, it's a technique called chirp spread spectrum modulation. So like most forms of wireless communication today, it relies on modulating radio waves. Now we have a lot of techniques we've developed over the years as humanity to do this, including the classic amplitude modulation, phase modulation, frequency modulation, which you might have heard of AM or FM or PM. You can combine all of these. A common technique in digital radio is QAM, quadrature amplitude modulation. All of these are forms of modulating a signal on top of an analog carrier at some frequency and encoding some data into that. So LoRa uses a bit of a different technique, or I guess you could consider it a form of frequency modulation. Essentially, it creates chirps, which are a linear ramp in frequency, from a low frequency to a high frequency. And by chirping these chirps, it's easy for a decoder to find this long ramp. So one of the problems of a lot of wireless communications is how do you work at low signal strength? So lower signal strength means your transmitters need less power, they save more battery, and also you can decode them from further away, both of which are things that are very important to LoRa. So this chirp modulation creates a linear wave through the spectrum, and demodulators can look for that and find it relatively easily, even through the noise. So LoRa is able to demodulate down below the noise floor, which is pretty unique among communication systems. Another neat thing is that it encodes a lot of data in these chirps, between 7 and 12 bits of data. So that's comparable to something like 4096 QAM, which is a really high bandwidth encoding used in Wi-Fi, which also encodes 12 bits, 4096 symbols. Now don't get ahead of yourself, it's not nearly as fast as Wi-Fi. The downside of this modulation is it's extremely slow. So LoRa's capacity is measured at best at about 50 kilobits per second, which is slower than the fastest form of dial-up. And that's at its best. At its worst, it's measured in bits per second. Usually though, messages on LoRa are limited to around 50 bytes of data, which is perfectly fine if you're trying to measure sensor data even at a relatively frequent interval like once a minute, you can get your sensor data transmitted back with just a few bytes. So now that we understand what LoRa is and why it's so useful for long-range, low-speed communication, let's see if I can get my LoRaWAN Gateway set up. So now that my Pi is set up with Raspberry Pi OS, it's time to see about the software. Now, Electro provides software for this board on their GitHub, and their software is essentially direct from Semtech, who's the maker of the chip. Unfortunately, Semtech software is rather old. It was last updated in like 2019, and it's kind of crusty around the edges. So I made a few changes, especially in the make install, so it actually installs itself properly instead of just leaving itself in /home/pi. And also added support for IPv6 because they were hard-coding AF iNet sockets. So this is what my fork looks like. You can see all the changes I made if you really want to. But I'm just going to go ahead and copy that link because we're going to use this. So over on my Pi, I've named it LoRa the Explorer. I'm just going to git clone. And then we'll go in there. And we'll do make. After that, we do sudo make install, and that should work. So now that's compiled the code from Semtech. It put it in user local bin, which is a good place to put binaries, and it created a configuration directory for it in Etsy LoRa packet forward, and also a systemd service and registered and all that good stuff. So now we need a global config file for the Semtech packet forwarder. This is what's going to forward our LoRa packets back to the cloud. So we have some examples here to start from. So depending on what region you are, you might need the EU 868, or you might need the US 915. Realistically, you're going to need this file or this file, unless you bought one of the USB versions instead of the spine, then you need the USB ones. Our gateway also needs an EUI 64 address. That's kind of like a MAC address, but 64 bits. There's a script here that will generate one from the MAC address of the Raspberry Pi, which is handy, so we don't have to generate random numbers. So to start, I'm going to start with US 915, and I'm just going to copy it to globalconf.json. So now I have a globalconf.json. Now I'm going to update the gateway ID. So it decided to use this address. That's the MAC address of ETH0, by the way. The Raspberry Pi, ETH0 is actually its name. If you don't have an ETH0, this script will get very confused. So now let's take a look at the changes I made to my configuration file for my setup. They may be different for yours, so take a look at this. So this is a diff, so we're looking at a diff here. And so the gateway ID was populated by the script. I changed my server address to be chirpx.panelot.net. Later in the video, we'll find out what this address is. I increased the push timeout from 100 to 1,000. This is because I was testing with the Things network. And with the Things network, I was using their cluster in London. It was about 100 millisecond round trip. So I was losing some connections because of that. Bumped it up, not a problem anymore. And I also changed the GPS to be S0 because it defaulted to not having one. So once we're happy with this config, we can copy it into Etsy LoRa packet forward, and we can start the packet forwarder. And now we can start it with system control. So this is going to go through and it's going to reset the chip, start it up. Once your cloud service is running, this should respond with push-ax and pull-ax. For now, though, it's just going to sit there trying over and over. So now our LoRaWAN gateway is set up. So you might have noticed I've mentioned LoRaWAN a few times in this video. So what is LoRaWAN and what makes it different from just LoRa? So LoRa is the chirp spread spectrum modulation technique developed by Semtech, or they're now Semtech. And that is essentially a way of transmitting binary data over the air. But it's not a protocol. We can't speak LoRa. I mean, we could speak LoRa, but it wouldn't be terribly useful to us. We need some sort of higher level protocol to give meaning to these bits of data. And there's a few protocols out there that are based on LoRa. So Meshtastic is another protocol you may have heard of that's based on LoRa. And that's a system for sending text messages in the range of several kilometers point to point between people. And that's extremely useful, but that's not what we're looking for here. LoRaWAN is a technique for sending data from low power sensors to moderate power base stations and having those base stations relay that data to the cloud. So LoRaWAN was also developed by Semtech and the LoRa Alliance for wide-scale communication. The goal for LoRaWAN is to have nodes essentially everywhere so that a sensor is always within range of one of these nodes. And since the range is something like a kilometer or two, it doesn't have to be that close. You don't need a ton of nodes to make this work. But because it's cloud-based, all of the data gets tunneled from the gateway back to the cloud, and that means that we could conceivably have a LoRa sensor node or transmitter, move it all around the country, and if we had a great enough network of gateways, we'd be able to get our data back home safely. Now, there are two networks that implement this in practice in the real world. There's the Things network, and there's the Helium cryptocurrency, I guess you could call it, which is sort of a way to give a business model to this thing, paying people for running these gateways. But there's nothing stopping me from running my own cloud. So if I have a gateway at my house, I could run the cloud at my house too. Suddenly I have a fully self-contained LoRaWAN node in the 1 kilometer radius around my house. And I don't know about you, but I don't really need sensors to talk to me more than a kilometer away from my house, so I'm pretty happy with that. Another neat trick from LoRaWAN is that all the communications are encrypted and identified. So every node has a unique ID and unique key that's generated and programmed into it at the factory. Usually they have a QR code sticker on them, or for devices we program in Arduino, we write it in ourselves and we know what it is. And if we put those numbers into the cloud, it can establish a session, create session keys, and the sensor can securely send data. But this encryption is done all the way back to the cloud. The gateways aren't involved at all. So we don't have to trust the gateways with our sensors. We just have to trust that the gateways exist and are in range to relay our data. LoRaWAN also gives us the ability to send packets to port numbers. So it has an 8-bit port number, so we can send up to 253 different ports, kind of like a UDP port message. It's not session-oriented like TCP, but we can send small packets of about 50 bytes to up to 253 ports, which is plenty for this kind of low-power sensor stuff. So in my case, I'm going to set up the sensor board later in the video. I can hook up multiple sensors to it. Each sensor can broadcast this data to a different port number. All that data makes its way back to my gateway, ultimately my cloud, and from there we can get to Home Assistant. So future Apple art here, I actually realized in editing, I forgot to mention you can send data down in addition to up. So one of the big differences between LoRaWAN and some other protocols is that we never wake the device up. So the device cannot be woken from sleep except from its own timer. So if we want to send a downlink message to a device, we queue it in the cloud on the Chirpstack, and we just wait for it to respond, and then once it sends a message up, we have a few seconds where the device will stay awake and let us send messages back. So if we want to reconfigure a device, say we want to tell it to send data every 5 minutes instead of every 30, we have to wait for that next 30-minute ping, and as soon as we get that data at 30 minutes, we have a few seconds, send a packet back down, the node will receive it, we're all good. So you really can't use this for real-time interactions, but you can do this for things like changing schedules, changing settings. It is bidirectional in that sense. So now that I have the Electro Gateway set up and running, let's get the open source Chirpstack LoRaWAN cloud set up. Get our data piped into Home Assistant. So I hope the architecture of LoRaWAN makes some more sense to you. We have the cloud service. That's where all of our encryption happens. That's where managing of devices happens. Then we have these gateways located potentially all over, or maybe just one, that are sending our traffic from the airwaves back to the cloud. If you have a large property, you could put these in a few different places. The range is really good though, so I'm going to have a hard time finding a need for more than one gateway locally. But it's certainly possible. Now we already set up one gateway earlier in the video. If you set up more, they'd follow the same process. And so that's the Semtech packet forwarder, the first step. There are 3 or 4 other pieces of software we have to make work to integrate this all together. So there's Chirpstack itself. This is what processes the LoRaWAN packets. Now Chirpstack uses MQTT to transport its data. So if you don't already have an MQTT server network, you'll need to set one up too. I'm going to assume you already have one set up from Home Assistant. That's what I have. Then we need a way to get the packets from the Semtech packet forwarder into Chirpstack, and Chirpstack provides a bridge for this. It listens for the UDP protocol from Semtech and converts that to the MQTT protocol that Chirpstack expects. You can run this bridge either on the Raspberry Pi or the server that runs Chirpstack, And actually, if you want, you can run all three of these parts, the Semtech gateway, the MQTT server, the packet forwarder for Chirpstack, and Chirpstack itself, all on the same Raspberry Pi if you want. You can follow their instructions for Debian. They have packages compiled for ARM64. So coming over here to the Chirpstack instructions, I clicked on Debian Ubuntu. It says Ubuntu 22 and Debian 11, but I tested this on Debian 12 and it was just fine. Now I created a container in Proxmox. You don't have to. You could run this directly on the Raspberry Pi if you want, but that's what I did. So I'm not going to walk through the exact commands here because this is actually written very well. But you can basically follow through their commands to get the software set up. So you add an apt repository. They have packages for x86 and for ARM64. You install the gateway bridge. That's what goes from Semtech to MQTT. You configure it for your region. And then you can start it or enable it. Then you can install Chirpstack itself and create a config file. So I'm going to show you now the configuration settings that I used for my config. They will hopefully help you create your configs. So first we'll look at the gateway bridge. So this is all default. Type is Semtech UDP. So I changed UDP bind from 0.0 to : just to enable IPv6. And then down here it defaults to EU868, I think, but we need to change it to a frequency plan and a channel number. So in LoRaWAN, every gateway supports 8 channels of the 64 possible frequencies. I guess the exact number depends on what region you're in. In the US, there are 64 possible frequencies. They're broken up into 8 channel groups. So a given LoRaWAN network chooses one channel group for the entire network. This is 8 frequencies. I have chosen channel group 1 for this purpose. It's the same one that the Things network uses. That's why I chose it. A lot of software defaults to using this channel group. The individual devices will use one of 8 frequencies in the channel group, but they'll use a different one for each transmission, and the gateways support all 8 at the same time. So here US 9151, so that's the second because 0 is the first. And then in this case, my MQTT server is on localhost, so I just put that in. And I'm running without encryption right now, or authentication. So you would put in your MQTT information here for your MQTT server. So next up we have the Chirpstack config for the app itself. So going all the way down, there's a network identifier. So in LoRaWAN, transmissions include a network identifier, which is 3 bytes. This is how you identify like individual networks. So Helium has one, the Things network has one. The Things Industries, who runs the Things network, supports multiple of these. If you're just testing on your own, you're supposed to use the number 0 or the number 1. Those are both reserved for testing. There's no organization that publicly assigns these, so it's kind of messy if you use other numbers. So then I come down to enabled regions, and I commented on everything except US 915.1, which is the frequency I'm using. So further down, I again changed the bind from 0.0 to the IPv6 version. There's a secret here you're supposed to replace that you probably should do. And then I'm using localhost again for this. Again, you can use whatever MQTT server you're using. And so that's what the basic config of Chirpstack looks like. Let's go into the GUI and see how it looks in the web interface. So once you get Chirpstack running, it's on port 8080. The default username is admin and admin, and let's go. So Chirpstack is one of these new fancy applications that's designed to scale. So it supports multi-tenant, multi-application per tenant. I'm not operating this big of a scale, so I'm not using multiple tenants. I'm only using one application, and it's kind of big for me, but it is what I have. So in my tenant down here, I can look at my gateways. So I have this guy here. This is LoRa the Explorer I created earlier. I'll walk through how to set that up in a minute. And then I have device profiles. So I created a device profile for a basic node, and again, I'll walk through that in a minute. And then I have applications. So I created an application called Home. Within the application, we have devices. So each node has a node profile, it has a name, it has an EUI, and it's bound to an application within a tenant. So that's kind of the hierarchy of how things work. Each application also supports integrations. This is where data goes. So if you're using this kind of at scale, you would have sets of sensors. Each, I guess, type of data you're doing or each backend would have its own application. So if you have some sort of data monitoring, and then you have some sort of other project that's using LoRaWAN separately, there could be separate applications within your tenant, and each of them would have its own devices assigned to its application, and their data would go back to the backend. In my case, all the data is going to MQTT, so I just need to have an application there, so I created Home. If I had more than one location, I could do that. It's up to you, it's flexible. The gateways are not bound to an application, they're just bound to a tenant, so they'll handle all the data from all the different sensors. One quirk I found here that drove me crazy is all of these app integrations you can choose plus to add, except MQTT, just says get certificate. And I could not figure out why I couldn't add it. And it turns out it's just enabled by default, so there's no need to add it. If you want to use MQTT, the MQTT integration, you just connect to the same MQTT server that Chirpstack's already using. The data's all there. So now I deleted my gateway, so let's go through the process of creating a gateway. It's pretty easy. We just click Add Gateway. We give it a name. So I've got LoRa the Explorer, and I just need the EUI64. So over here on LoRa the Explorer, I have this as my gateway ID, so we'll copy that, paste it in. You can give it a description if you want. It's in the cat's bedroom. It's named LoRa the Explorer. It's located in the middle of the ocean. This will figure itself out in the future, and we submit. So now if I go back to my gateways and I refresh, it should pop up within a minute or so. There we go. It took it about a minute. It's there. If I click on it, that's another reason these things have GPS. The GPS of the gateway gets sent back here. It's possible if your application wants to try to triangulate sensors, all the data is available in the integrations to do so. If you want to do that, I'm not doing that. So while I am going to demo a completely custom LoRaWAN node using the Electro board, I actually went out and I bought a temperature and humidity sensor just to see what a commercial off-the-shelf device looked like. This was not that expensive. I'll put the price on the screen somewhere. It comes with a battery that lasts basically forever, and it's got temperature and humidity, and we're going to pair it. The box it came in includes all the numbers I need, all the security codes, so I'll just have to type those in. So I stopped and read the manual for this. This guy has temperature and humidity. It's pre-configured with the frequencies of the Things network, so me using the same frequencies is a good idea. So before we push the button on this guy, we're going to go into Chirpstack, configure a device type for this model that tells it how to decode the data. Then we're going to create this specific device with the EUI and all those other information. Then we can have it bear. So here in device profiles, we can create types of devices. So this is like a device model, and it includes information on how to decode the data. You can create templates up here if you have multiple tenants. I don't have multiple tenants, so I'm just creating profiles here in my tenant. So this is a LHT65N. So that's my name. So region is going to be US, and we're going to be on channels 8 to 15. The LoRaWAN version is 1.03 in this case, and we're on parameter set A. And everything else is good. And we're not going to allow roaming. So roaming is a neat feature of LoRaWAN where your network can roam with other networks. So I could, for example, roam with the Helium network. So my sensors are on my own network when I'm at home. When I go out, they use Helium. Likewise, people could use my gateways as Helium gateways. I'm not going to set that up, but it's possible. So that's this page. Next we have join. Most of the time we use OTAA, which means it's automatic. We're not manually setting cipher parameters. Class B and Class C devices wake up less frequently. This is not a Class B or C device. And then codec. So this is how to decode the data. If we say none, it's just going to keep it as binary. We can come down here and say JavaScript functions, and then we need to write a decode function. I bought this node from Dragino, so I can come down here and look for their decoder, LHT65N. I want the Chirpstack 4 decoder. We'll just go raw, don't translate it, and we'll just copy and paste that in. So let's submit. And so now the LHT65N with its codec is created. So I go to Applications, Home. I don't have any devices yet, so let's add a device. What are we going to call this? Nope. Now we need some information. So we need the device's EUI64, and this is called the join EUI64. Sometimes it's also called the app EUI64. And in my case, they came on the inside of the box. So I'm going to type these out. There is a QR code that has the device EUI64. It doesn't include the security code, which I'm going to need later. And device profile, we're going to pick LHT65N that we already created. And device is not disabled because it is real. Let's submit that. Now it's going to tell us it needs the application key. This is the security key. And we'll type that one out. So now that our device is created, we can tell it to join. When it joins, it's going to send out a broadcast, and it's going to try to find a gateway that can decode its app ID. And since our gateway has already been configured, it should be just fine. So I should be able to just push the button for 5 seconds. Let's see if this works. 2, 3, 4. Oh, it's blinking. Oh, look at that. It checked in. So this is what it looks like in MQTT Explorer. I'm connected to my gateway, Chirpstack. So the US 915 topic has information that's not relevant, but that's internal to Chirpstack. And under application, I have the UUID of home. Here is the UUID, but that's the UUID of home. And then I have device, and then I have the MAC address of the device, or the EUI of the device, and event, and we had an uplink. And so let's look at that uplink data. So the data is that garbage. And then decoded, we get battery status 3, temperature, there. So I just got another packet so it overwrote the data. So humidity is 33, temp DS, that must be the external sensor. And then SHT, that must be the internal sensor. Now, this guy's fun and all, but I'm going to build my own node with this board Elecro sent me, show you how this works too, so you can build your own nodes, mix and match with off-the-shelf nodes in your LoRa network. So next, I'm going to make my own sensor node to send data to LoRaWAN, parse that data back out in MQTT, and get that into Home Assistant. Now there are a number of chipsets you can buy that do LoRa. Some of them also do LoRaWAN. The chipset on this board is the RA08H. It does LoRaWAN. It's entirely self-contained. We just have to configure it using AT commands on the serial port, and it's not that hard to do. Electro has 2 versions of this board. One version of the board just has the R808, some level shifters, and the antenna jack. You can get that if you want to use your favorite microcontroller. If you don't want to use your favorite microcontroller, they also have this board available that I have, which includes the RP2040. That's the chip from the Raspberry Pi Pico. And this acts just like a Raspberry Pi Pico. You can program it in Arduino. So we got the Pi Pico, the RA08H, which is the LoRaWAN chipset. We got some sensor interfaces on the back. There's a connector for a battery. I actually have a battery, so this is a single cell lithium battery. They're super common, easy to find. Just plug it right in. And it's got a connector for a solar cell too. So this could make a really great outdoor battery solar powered node. Never need to change the battery. If your solar panel is big enough, you're not transmitting forever. So that's what I got for this project. Going into this, I'm going to assume you've already set up the Arduino environment for Raspberry Pi Pico. There's plenty of guides on that part on the internet. Once we have that set up, we can start downloading code to this. Now there's no library for the R808 that I could find, so I wrote some of my own functions. If you go to my GitHub page, there's some example code you can start from on how to transmit data. So coming over to my GitHub, this is currently what the RA08 looks like. So LoRa RA08. And basically each of these folders is an Arduino project. So Arduino demands that the INO file is in the folder of the same name, so the node at INO has to be in the node folder. So I've got 3 Arduino files. So the first one's called app key, and what this one does is it generates a random EUI64, so using the random function, and it generates a random dev EUI, app EUI, and then an app key, which is a 128-bit random number that's used in the cryptographic process. When you buy a LoRa node, they're supposed to come pre-programmed with these numbers. The RA08 comes programmed with all zeros, so not terribly secure, is it? But we can just override it over the serial interface. So just download this, run it once. It'll spit back out your EUI 64s and the app key. You'll need those later, so save them. Once you've done this once, the keys are set. They're stored in Flash, so you don't have to run that program again. Also, of slight note, I'm using the RP2040's hardware random number generator. If you are not using the RP2040, you have to comment that out and use the regular random function, which might not be as good. So up next, I have a simple debugging program that just passes AT commands back and forth. Basically, the RA08 is a serial port. The USB is a serial port to the computer. It just bridges those two so you can type in commands and read them back and see how they look. Currently, my third program is called Node, and this program is just going to send a number every so many seconds. So currently that's set to 10 seconds, so 10,000 milliseconds. So all the way at the bottom, we have this function RA08 XMIT. So that takes a byte array, and it takes the port number and the number of bytes and some other information, and transmits that over LoRaWAN. So this is currently just an example. Every time it transmits, it increments its counter. So we're going to get a 2-byte value. That's the number of times it's counted. If you watch it carefully, it's also blinking. So we'll do a long blink for a 10 and a short blink for a 1. This is how I do range testing. I carry this around with me. I look at it closely. I'm like, that was a 22. Then I get back home, I look at, did I receive number 22? If yes, then it must work at that range. So I also wrote a simple decode function for this. This is going to be on the GitHub as well once I'm done with it. Basically, you get decode uplink, which has the uplink port number and a byte array, and you return a JavaScript object that has all your data. So I'm just saying if fport is 1, then we decode it as a 16-bit integer and return the parameter count. So coming over here to Chirpstack, let's add a device profile for my custom counter. And it's in the US region again, channels, all that good stuff. And then we want a codec. We want to use JavaScript. We'll paste that in. So like I said, decode uplink, Chirpstack will give us an input that includes these 3 fields. So bytes is a byte array. Fport is the uplink port. That's 1 to 253. And device variables. So we just return an object, and then we can add any variables we want to the object, and that gets sent to the output. So I'm just taking this as a 2-byte number because that's what it is. It's in big endian. So let's go over here and let's add my device. So here's what I ended up programming into it. So that's my dev EUI, and the device profile is a counter. So let's submit that, and we need the app key. So I have this thing configured to join every time it boots up, so that assumes it will stay booted up the whole time. You don't have to do that, but I'm not sure how to persist the join information into non-volatile memory on the RA08. So maybe someone who wants to read the datasheet more could figure that one out. So I'm just going to unplug it, and when I plug it back in, it'll do a join, and then we'll see it come up. Okay, so I refreshed a few times. This took maybe a minute, but it is up. So we can look at it, and it sure is up. So popping over here to MQTT Explorer, that's my EUI. So we look at the uplink data, and object count. There we go, count 1. Oh, now count is 2. So this is basically how I'm creating LoRaWAN nodes for the sensors I have. So using the RA08 board, either the one with the Pi Pico or without, I can set up some sensors, read the sensors in, convert it to binary bytes, send it over LoRaWAN, decode the bytes in JavaScript. That gets me to MQTT. So now the data is in MQTT. We just have to get it into Home Assistant from here. So finally, we've set up the gateway, we've configured Chirpstack, we've configured all of our codecs for all of our devices, we've joined our devices, now our data is in MQTT, we can finally get it into Home Assistant. So here's an example of what I want to happen at the end. So this is a value that came from the sensor, it's just the counter that counts up. I have another version of it where I'm calculating a floating point value, some sort of scaling. I assume you'll probably want to send data that has decimal places instead of just integers. The easiest way to do that is just to multiply it by like 10, 100, 16, 256, something like that, and then divide it back out in JavaScript. So instead of trying to send a full range floating point number, either a half or a single or double or whatever, so you just make it a fixed precision single point, send it in binary, convert it back. So we're going to have that. And then I also want to get the RSSI and signal to noise ratio from our reception here. So just showing what I mean about this decode float. So if I take this number that's a 16-bit number and I just divide it by 100 and tell JavaScript it's a float, then we could say this is now a percentage, maybe it's a degree Celsius. So for example, if you want to send degrees Celsius, you could just multiply it by 100, send it as an integer, and then divide it by 100 when we get there. So we get 2 decimal places, hundredths place. So for this setup, we have to use manually configured MQTT entries. This means we're going into configuration.yaml. If you're the kind of person that has a lot of structure to configuration.yaml, you probably know where your MQTT entries go. You might have your own file for them. I don't know, but I'm just going to put them straight in configuration.yaml. You'll probably know where this goes if you're doing something more advanced. I've also got the documentation from Home Assistant up here. So it says we should start with an entry that looks like this. So I'm just going to copy this and paste it in. And so we're just going to call this the counter. Counter value. So now we need a topic and we need a way to parse it. So coming over to MQTT Explorer, here's our data, here's the up. So I can just scroll on this side and it's a long string here and I can just click copy. Don't have to worry about figuring out all those UUIDs. So we'll come over here and we will paste. So now the problem is, if we don't tell it how to parse this, it's going to assume we can just turn it into a number. So Home Assistant is going to get this topic, and the value is going to be this huge JSON struct. So we need to un-JSON the JSON struct. So Home Assistant has a much longer example here of all of the different options we can have. So we can use unit of measurement, we can use value template, so I'm just going to copy these two. And in value template, we use a Jinja template. Jinja is really commonly used in Home Assistant, and so we can parse values out of the JSON. So if we come over here, so that's the root objects, that'd be value JSON. And within that object, we have an object called object. And we have an object called count. So we need .object.count. Value JSON.object.count. So let's save that and let's see how this goes. So there we go, we got a counter value of 3. So what about the rest of those numbers? They might be a little bit harder, 4, but a little bit harder to parse. So now if I want to make a new one, we'll just copy and paste this. So now instead of value, we want percent. And that one can be float. And we can add a unit of measurement. And while we're at it, let's do the other ones as well. So this is going to be RSSI, MDB, and SNR. Also in DB. So back over here at MQTT Explorer, so we have the data from object, count, and float. And our RSSI and SNR are within this RX info structure. So that's an array, and it shows all the different gateways that received it. And so we need RSSI and SNR out of the first receiver. I'm just going to assume that the first receiver is the good one. So this would be .rxinfo 0.snr. And this one would be .rxinfo 0.rssi. So let's see how this works. So there we go, we got an update. So it's 10 is the value, divided by 100 we get 0.1%. So we have 2 decimals there, and we had an SNR of 10, which is positive, which is pretty good. LoRa can go down to like -10 or so without problems. And our RSSI, which is the signal strength, is 87 dB, negative 87 dB. So now we finally got our data into Home Assistant where it belongs. So thanks for sticking with me on this whole video as I go through the ins and outs of setting up a LoRaWAN system completely self-hosted for all of your IoT sensors in Home Assistant. Hopefully this video inspired you to do something cool, monitor some faraway sensors, do something like that. Of course, you can buy sensors for LoRaWAN off the internet. I bought this temperature and humidity sensor. There's a lot of sensors for things like soil moisture, soil pH, things like that. If you're doing gardening, this could be very useful for you. I found someone else on YouTube who's used LoRa for monitoring his mailbox. It's too far away for a lot of other protocols, but LoRa works just fine. Or maybe you want to build your own thing with a node board like I showed in this video. It's all up to you. If you want to buy any of the products I used in this video, links are down there in the description. Thanks to Elecro for sending me this gateway module to play with. I had a great time with it. Hopefully you guys learned something too. We're losing him. If you want to join my Discord server, link down below for that as well. If you're interested in tipping me for any of my content, if you find it useful, link to Ko-fi down below. You're free to donate. I always appreciate it. And as always, I'll see you guys on the next adventure.